Welcome to a tutorial on the 8085 interfacing with data converters. Okay, so here we're gonna this is a part 2 of the previous tutorial, as you can see, and we're gonna go on with the interfacing part over here, okay, as to how you can interface the 8085 with the DA converter. So back in the previous tutorial we used the DAC chip 1408A, okay, acting as the digital to analog converter along with an op-amp. Okay, so these two things just give us the analog voltage output. Okay, and we are going to implement some few more peripherals with the 8085 over here in order to complete the interfacing. Okay, so now in order to approach this we need a problem statement so that I can give you an example as how you should approach a problem, okay, whenever you're supposed to interface this kind of a circuit. Okay, so let's bring our problem statement over here. Okay, so here we are with our problem statement. Okay, so it says, now there are two parts to this problem statement that we got over here. Okay, so part A says that design an output port with the address FFH to interface the 1408A DA converter. Okay, and it's calibrated for an output voltage range of 0 to 10 volts. Okay, so we need to keep this in mind. And okay, so we know that this 1408 DA converter chip that we got over here, okay, this chip doesn't have any kind of enable or disable pins on itself, okay, and that we just saw in the previous tutorial. Okay, so we need to configure a circuitry, a hardware, so that we can just enable or disable its inputs and all. So that will just come to it later. And the next part says that we need to program the 8085 to generate a continuous ramp waveform. This is another important point over here in the problem statement. Okay, so now keeping these things in mind, we can just get started with our circuit first. Okay. Alright, so I just brought here the pin diagram of the DAC 1408 just for your convenience. Now you can see all these pins over here, out of which, the pin 5 to that of 12, it just serves as the input, serves as the input lines for the corresponding digital input bits. Okay, it's got 8 bits of digital input code that it can basically take, since it's an 8-bit DAC. Okay, and apart from that, we can see that we got the reference, the ground, and the 2 input pins for the voltage and the output and compensation pins, but nowhere we can find any pin for enabling or disabling the chip. Now while working with the 8085 and in order to make the provision of accessing this particular chip only when the address of FFH is given out by the 8085. Now in order to incorporate this facility, we would need to connect some other device along with the DAC over here, maybe a latch chip. Okay, yeah, you can just say that. Now a latch is quite a good getaway under this sort of a situation. Okay, so let's just configure the DAC in the way it should be used in this particular circuit. Okay, there you go. So now we have the 1408 chip, DAC chip that is, configured, or rather being used over here in the unipolar mode. Okay, so this is basically the unipolar mode in which we're using the chip. Okay, and now since we need to activate this chip under the address of FFH, so we just thought of connecting or using a latch chip along with the DA converter that we got over here. So let's just use the latch chip named LS, or rather 74, okay, 74LS373 latch chip that is also used for address data bus multiplexing and demultiplexing with an 8085. So let's just use this particular chip over here along with the DA converter. Okay, so here we've incorporated the 74LS373 latch chip along with the DAC 1408A. Okay, So this is how we just connect the latch with this DA converter. And finally we need to interface, or rather connect these two with the 8085 microprocessor circuitry. Okay, so let's just take a look at how we do that. Alright, so here we are with our designed hardware. Okay, so as you can see in this particular circuit diagram, that we've got the 8085 connected with its latch chip, that is 74LS373 over here for latching the address coming from its lower order address data buses. That's 80 through to 87, and on the right hand side we got the DAC 1408A interfaced with the 8085 microprocessor by using the latch LS373 in the very same way that I just told you all. Okay, now you can see that the second latch chip, I'll just call this one as latch 1, so that is L1. Okay, and I'll just call this one as L2. Okay, now the latch chip, that is L2, connected with the 1408A, over there we can basically see that the output of the latch just joins in with the binary input of the DAC chip. Okay, and on the other hand we can see that the data coming from the 8085 joins with the input lines of the latch chip L2. Okay, and now in order to decode the address, we've just used the pins we've just used the pins that is 00 through to 07 of the latch chip L1, okay, fed into an 8-input 8-input NAND gate over here, that's gate G2. Okay, and we've also used a negative input AND gate G3 for sending the decoded address for enabling the latch chip L2 that we got over here. Okay, now you can see that. And in order to provide the other input of G3, we've used an AND gate, okay, that just takes in the write bar and the input output memory bar signal of the 8085 microprocessor as an input. Okay, that's gate G1. Alright, so that was the entire description of the hardware involved over here. So as the first part of the problem says that we needed to design an output port with an address FFH, okay, for interfacing the DAC 1408A chip with the 8085. And now you can see that we also need to calibrate the DAC for the 0 to 10 volt output range. So that is basically done over here, where we've just kept the R14 and R15 both at 2.5k ohms. Okay, and the op amp that we got over here has a reference or a feedback resistor RF having a resistance of 5k ohms. Okay, and including a capacitor of 15 picofarad at the in between the pins 16 and 3 over here. So this is just the DAC chip is just set up for a 0 to 10 volt output range. Okay, now we know that practically the full scale output of this DAC 1408 is basically 9.961 volts. Okay, so this is basically the full scale output. Okay, so this is the full scale output of this particular chip. Now this is approximately equal to now this is basically approximately equal to that of 10 volts, so we can just take this value practically for our all sorts of practical applications as such. Okay, so now keeping that in mind, now we can let's check the circuit, okay, whether it just works off the address FFH or not. Okay, so whenever let's say we have a code, okay, we have a code written in our program for the interfacing of this hardware. So whenever we need it, or whenever the 8085 basically sends out the port address, okay, the output port address FFH from its lower order. Now you can see that since the port address is just an 8-bit data, okay, so we've just used the lower order address data bus. Okay, we've not used the higher order higher order address buses, that is A8 to A15. So you can see that they're unused over here. Okay, so whenever the FFH address would appear on the lower order address data bus from 80 through to 87, okay, then they would enter into the latch chip L1 over here, okay, and since the ALE at that very moment would be set at a logic 1 level, so this would just keep the latch chip enabled, okay, and whatever address would appear on the input, okay, that the same thing would appear at the output as well. So as soon as the address is FFH, okay, at that very moment what happens is that the output now the latch chip L1 is transparent at this moment, okay, so it's L1 is basically transparent. I'm just gonna write that down over here at this moment, okay, and so the address FFH appears on the output pins of L1 as well, and it enters into the gate G2. Okay, now after that, since it's an output operation, okay, the 8085's input output memory bar pin would output a logic 1 voltage level, and the write bar pin, and since it's an write operation, we need to send the data, so the write bar pin would just go to logic 0 level, okay, in order to enable the process. So with these inputs to the gate G1 would have a logic 0 output voltage, okay, fed into one of the inputs of G3, and with the address FFH appearing at the input of the gate G2, okay, which is a NAND gate, it will just all the bits over here at the input of G2 are logic 1, okay, so the G2 would output logic 0 voltage level as well. So both logic zeros into the gate G3. Now you can see that the input of the gate G3 is basically basically an active low input, okay, so the input gate G3 is basically active low in nature. So whenever we have zeros over here, it gets converted to 1, okay, so it just gets complemented, and those ones are sent by this AND gate G3. Now you can basically understand that whenever we have two zeros falling in, okay, so both zeros get converted to ones, okay, by the input of the gate G3, and whenever these two ones are ANDed up, we get a logic 1 at the enable input of the latch chip L2. So as soon as the latch chip L2 is enabled, okay, now by this time what happens, now we can see that the latch chip enabled, the latch chip L2 over here, it gets enabled at this time. Now immediately before the L2 chip over here gets enabled, what happens is that the lower order address or data bus, that is 80 through to 87, okay, it gets ready to output the data, okay. So whenever the input out, now since it's an input output operation, so as soon as the logic level on the input output memory bar pin goes to logic 1 and the write bar pins goes to logic level 0, at that very moment the lower order address data bus stops sending the address FFH, and now at this moment it is sending a data, okay. So it's become the data bus, now it's behaving as a data bus. So at that very moment the ALE pin now goes to logic 0 level, okay, and at that particular moment the address that it's sent, that is FFH, it becomes latched by the chip L1. So the address is latched at the output of the latch chip L1, and that basically maintains the address. And now the data that is sent by the lower order address data bus, okay, it reaches the input of the latch chip L2, and as soon as it receives a logic 1 on its enable input over here, okay, this chip gets transparent and sends the data, that's the binary 8-bit data from the 8085 microprocessor, into the binary input pins of the DAC 1408A chip, okay, that's the pins number 5 through to 12. Now, whenever it receives this input binary code over here, the chip quickly starts its DAC operation and outputs the corresponding output voltage from the output of the op-amp that we have connected with the chip also. Okay, so here V0 would serve as our required output. So that's quite an extensive explanation of the entire working process of the hardware. So now we have the second part of the program, of this video actually, where we have to write a program to enable the 8085 to generate a continuous ramp waveform. Okay, now before going to that, let me tell you what a ramp waveform basically is. So if I might draw a graph, okay, and if this is the voltage versus time. So in a voltage versus time curve, if the voltage versus time curve characteristic becomes something like this, okay, or is the line got a bit crooked, don't mind at my drawing, I know it's awful. Okay, now if the voltage time curve is basically a straight line, so you can see that this line is very straight, okay, and it has a proper or it has a constant slope. If the slope of the line is just constant and it's just goes on increasing, if the voltage just goes on increasing with time, and it's just a straight line this way, then you can just call this as a ramp waveform. Okay, so this particular output type characteristic is basically what we call a ramp output or a ramp voltage. Okay, now it's supposed to keep on increasing with time. Alright, so now if we want the output of the DAC chip to just go on increasing with time, then we need to write a program for performing the same. So in this case, if we might divide the page into two parts, so this is obviously the opcode, okay, and we have the operand as well. Now here we are going to take a range, okay, now we are going to take a range 00H to FFH. Now we are going to start we're basically going to activate a counting process, okay, for the 8085 microprocessor, where it's going to count from 00H to FFH. Okay, so let's just do the same over here. So first up, we just load the accumulator. Okay, let's just write it in a bigger way so that it's easily visible. Okay, so first we load the accumulator with the data 00H. There you go. And okay, so before we do that, we need to declare another input statement over here. So MVI C. Let's just load the register C with the data, FFH. Okay, now what happens over here is that, sorry, I didn't maintain the columns. Okay, don't mind at that. Okay, so here I'm gonna give the instruction MVI C 00A, FFH. Okay, and then we got, well, MVI A 00H. Now we loaded these two data, and after we loaded the accumulator with the corresponding data over here, we need to send we need to basically send it to the output port. Okay, so what we do is that we'll use the out instruction, okay, out, and give the corresponding port address, which is FFH in this case. Okay, so this is our port address. Okay, there you go. Now after we just send the data contained in the accumulator to the output port for the corresponding analog conversion, okay, then we need to keep in mind that you see over here that the conversion time of the DAC chip, well, it could be more than the time required by the 8085 to execute the entire program. Okay, now how do we counter this problem? Yes, exactly. Now that's the reason why we took this particular, loaded this particular data of FFH into the register C. So we are going to start here, we're going to give a delay over here. We're going to introduce a time delay by declaring, or rather starting a loop for a counting process. Okay, so what we do here is that we just write here, okay, we're going to write here DCR C. Okay, so once when the output is done, the C register's data needs to be decremented once. So DCR C, and then we're going to give here, well, jump on no zero. If the count of the data present in the register C is not 0, okay, then the jump statement would be executed, and this is going to jump to the level J1. So I'm just going to give here J1. So it's basically a level now. I'm going to give the memory address later. So it's going to jump right over here. So this is J1. Okay, and next what we're going to do is that now after the output 00H is just sent to the DAC chip, now we need to increase the output, increase the value, okay, so that we could achieve this sort of a continuously increasing output voltage with time. Okay, so we're going to increment the value of A. So we're going to write here INR A, so that the A's, the content of the register A is just incremented once every time, okay, and then after that we just need to give an unconditional jump. So we're going to use another level over here, so that's J2. So this is the level, okay, J2, and we're going to jump right over here. Okay, there you go. So that's our program that we have, as you can see. Now, okay, so there's one mistake there in the program. I think I need to modify it. It's better if we just declare the MVIC command inside. Okay, so we need to declare it right over here. So MVIC, okay, FFH. There you go. It's because every time the loop gets executed, the data in the register C would not be loaded. Okay, if we would basically keep the if we just keep the MVIC command outside, okay, above the before the MVI command which initializes the data of the register A. Okay, so every time, now I'm going to explain what happens in this program. So every time the value of the A is the register A is increased by 1, okay, incremented once, we just start a counting process, okay, where we would load the register C with the data FFH and then go on decrementing it until the register C would contain 00H. So this just introduces a time delay. So by doing this, we're introducing a time delay so that the speed of the 8085, it just takes the 8085 to execute the entire program a little longer. Okay, it's because of the reason that the conversion time of the DAC chip might be more, or rather in fact it is more than the time in which the 8085 would just output or execute the entire program. So we need to give a delay in order to synchronize both the devices. Okay, and there's one more advantage of introducing this delay. You see, if we increase the delay, then in that case the slope of the ramp output voltage which we're going to receive as output, it could be decreased as well as increased. So by varying the time delay introduced over here, we can change the slope of the ramp voltage as well. So there are two advantages of introducing this time delay that we can see over here, and that's how our program is gonna work. Okay, so if you would need to load this program onto your kit, you need to just give the corresponding memory addresses. I'm not including them over here, it's just for your homework. And with that said, we just come to the end of this tutorial. I guess you've enjoyed watching it, and we're gonna see you next in the forthcoming tutorials as well. So till then, just keep watching, and bye bye for now.